Hi and welcome to number 3 in the expert series. A lot of people think that a char data type and a uint8 data type are the same thing and that they can be used interchangeably. They're not the same, and this video is going to look into a lot of detail as to what the differences are and the issues that stem from them. It's quite a long one, so get yourself comfortable and here we go.
But first, please subscribe to the channel, click on the like button, click the bell icon to get notified, and support me on Patreon if you can. There's a link in the description below.
If you think that the data type of char and the data type of uint8t in C and C++ are the same thing, then this video is for you. And I'd like to start by asking you a question. I want you to consider that error message from the GCC compiler, which says that there's an invalid conversion from const char pointer to const uint8t pointer. Now, let's factor out the const. It's an irrelevance because it's common to them both. So that's telling us there's an invalid conversion from one to the other. Now that is only meaningful if they are different. Because if they're the same, what does converting from one thing to another that are identical mean? That in itself is meaningless. Further meaningless would be that in order to try and do so, it constitutes a crime so heinous that the compiler is going to refuse to compile your code, because the conversion you have attempted between two things which are obviously and plainly different is invalid. So if you are a person who thinks this, then already the compiler is disagreeing with you. So this isn't an opinion piece as to why I think you're wrong. You are wrong. What this is going to go on and do, hopefully, is to look at why that might be, because you're not alone. Many people think that. So that's the good news. The bad news is that all of you who do are wrong. And we're going to consider several common possibilities as to why that happens. We're going to look at how you're wrong, meaning what is the actual difference then between the two. But more importantly, from a developer's point of view, is that what real-world problems can result from that mistaken thinking. So, moving rapidly on, let's look here. You see, here's one of these people that also thinks that char and uint8 are the same. Why people use two different terms for one variable type? Well, already you've seen that they're not the same, so that's why. And happily, C. Lawson, who you'd expect as a moderator of a group such as AVR Freaks, explains quite clearly that they're not the same, is that uint8 is an unsigned char, and char itself has no specification about its signedness. Now that might all sound a little bit woo airy-fairy for the moment. We're going to look at what that means in real life. So why is it that people think that way then? Because, well, a lot of us are used to dealing with strings, strings of characters. And so it's an easy mistake to make, isn't it? It's just from the natural language of it. Is that if you think that what you're looking at on the screen, for example, is a string of characters, then it's very, very tempting to think that if each one occupies a byte in a computer memory, then a byte and a char are the same thing. Now, there's also a historical reason for this, is that decades ago, probably even more, there were data transfer systems where a char actually only had 7 bits in it, and therefore That's where the sign issue comes from, because it had no sign bit, so you couldn't tell what it was. Whereas, unequivocally, as its name suggests, a uint8 is an 8-bit integer, so you're guaranteed to have access to all 8 bits, and there's no language or compiler confusion about whether it's signed or not, because quite clearly the U says it's unsigned. So a uint8 is an unsigned 8-bit byte. Okay? Now then, here's the elephant in the room, because that's history. In modern day computers, all, asterisk in case some wisecracker wants to tell me about the one system in a museum that doesn't work this way, all modern processors and CPUs can address memory as 8-bit bytes. I'm not saying it's the most efficient or the best, but the point is this, is that in the modern world, the last 20 or 30 years at least, an 8-bit byte and a char have ended up always occupying the same amount of space, which is 8 bits. So while they have had different historical origins, many people who've come to programming in the last 10, 15, 20 years, why should they think there's a difference? They're both 8 bits wide, therefore they're the same, aren't they? Well, no, they're not. And that's what the rest of this video is about, because I want to make it quite clear from this point onwards, for all the pedantic people, that this is not a debate about how much space they occupy. This is a debate about how you use them in the language, and how they are wrongly used in the language, and how that wrong use impacts on a number of problems. So, everybody happy? They're both 8 bits, okay? So it's how they're used. So even though they're both 8 bits wide, that doesn't make them the same. Because there is more to the use of programming language than just the data types. There are subtleties in the way that the language is used. There's issues of style, which is a very nebulous, subjective thing, but there are certainly issues of accuracy and or portability, which I'm not going to cover here. But now, also, in well-written code, there are issues of clarity and intention. And the great gurus like Björn Schustrup, whose name I can never pronounce, but the kind of people that write compilers and design languages, they put a lot of store into about, semantics of code and the meaning of code, not just the nuts and bolts, where people say, well, they're both 8 bits wide, so they've got to be the same. The point about style, clarity, and intention is this: that good style and clarity can suggest and or confirm the correct intention of a piece of code. To reverse that, one might say that poor style and lack of clarity can cause confusion when you're trying to work out what a piece of code is intending to do, which is always where you are when you're debugging, all right? So anything that helps that is good news. And that's the point about the use of the correct data type in its correct setting, is that it reduces confusion, it reduces potential errors both in your own code and if you're writing library code, the code of the users who are going to call your functions, and therefore it reduces incorrectly spelt development time. Now, in my personal opinion, this is one of the few opinion parts of this presentation, those things are the minimum requirements of a published library. And I generally make these kind of videos for a reason, and the reason for this one is that I find quite a few published libraries, open source, GitHub, etc., where the wrong data types are used, and their incorrect use produces confusion, not just potential errors, actual errors, and makes your development time much, much longer. So let's look at how long is a piece of string, because this is going to feature quite importantly in the subtle difference between the two data types. Well, if I was a lawyer, I'd give you a good lawyer's answer and say, well, it depends on what you mean by a piece of a string. Are you talking about a standard library std string? Are you talking about an Arduino style string class object? Are you talking about a C style string? Or are you talking about a kind of common English usage of, a load of the same things all occurring one after each other? Because depending on what you mean, it's a very different answer. And also depending on what you mean, it's perhaps a different data type. That's where we start to get into the nitty-gritty of this, because I'm going to concentrate mostly on what some people are calling a C-style string, which is a bit of a mouthful, but it makes that distinction. And the only thing you can accurately say about a C-style string is it's a contiguous sequence of bytes, important word that one, starting at some memory address, wherever, who cares, and continuing up to and including a null or 0 byte. Now, as you will see when we get into some live code later, it is the presence of that null byte on the end of that contiguous sequence of bytes that makes it a string. Without that null byte, it isn't a string. And that's really important that you understand that. So we're going to look at that in a little bit more detail in a second. That's, again, a bit of a mouthful. So most people say, a null terminated string of bytes or a null terminated string, and you probably hear me say that later as well. So let's have a look. We remember that again, don't we? Let's look at a data declaration like this then. The uint t pointer, which we're calling some data pointer, and a size type, which is some data length. Now, I don't know any programmer who would look at that and think, oh, that's a C-style string. Most people I know who know about programming would look at that and they'd think, well, obviously we're talking about some arbitrary block of bytes, and we probably don't know the length yet. So what some people would call a blob, a binary large object, or some people would call just a lump of data. Okay? Not a string, or especially not a C-style string. So now let's consider that definition. And conversely, almost every programmer I know, even the ones who should know better, like the ones who write public libraries, would look at that and think, well, it's obviously a string, isn't it? It's a C string. It's a char pointer. That's the standard type for a C string, and he's even called it my string for, to help the hard of thinking. Now here's the first point. Here's the first point of contention as to where these two are different. And it's in the meaning of what that is telling you as a programmer. Because if you think in that second one, if you make the assumption that that points to a C-style string, then that is where you are absolutely categorically and unarguably wrong 100% of the time. There may be a subset of that 100% where accidentally or coincidentally that does point to a string, but there is no guarantee in the language, in that code, in the mind of the programmer who wrote it. There is no guarantee that what that points to is a valid C string. If then you are in the habit of taking things like that and assuming that some built-in C function with str in its name, like strlen or strcopy or any of those things that operate on C strings, if you assume that that is going to correctly operate on that my string, then that is where you are going to cause problems. You are going to cause bugs. You are going to find bugs that other people have caused by making the same incorrect assumption. That is a pointer to some 8-bit bytes. That's all it is. If those 8-bit bytes have a length that you deliberately decided you wanted to be that length and then followed it with a null byte, then it would point to a string. That's a very, very, very specific case. And why does that matter? Read on. Imagine that you have a block of data like that. Now, I just picked that off the internet at random as an indicator, but it's actually quite interesting if you blow the picture up enough to look at the bytes that are in it. So there's a block of data that is, oh, I don't know how many bytes long, I don't know, and I can't care. The correct, and the only correct descriptor of it is as a uint8 t pointer with a size that describes how many bytes there are there. Because most absolutely 100% certainly not is it a C-style string. Because if you treat it as such, you'll find that the first byte is hex 14, 14, that's a decimal 20, which is in fact a form feed character, so not a printable character, causes like a screen swipe, and then it's followed by a null byte. Now, remember what we said recently, that null byte is what makes that, therefore, a 1-byte string. So if you thought that the rest of the data in there was part of your string, just because you had called that you had a char pointer called my string pointing at the front of it, then that's where you're wrong, because what you're pointing at is a single byte string with a form feed in it. Okay? Now hopefully you're coming along with me to this point and you're realizing why those two things are not the same, because the first data declaration described that block of data. The second declaration describes incorrectly those first 2 bytes, and they most certainly, even the most obtuse of you that are still with me, are going to agree that they are not the same thing. Okay then, well, why, you might be thinking, would anybody in their right mind use that second one when it's obvious that the first one is the only correct version? And that's a very good question, and that's the question I ask myself about 1,000 times, usually with a few swear words thrown in, when I discover that littering public repositories of code that is causing me huge problems by going wrong a lot. So just to remind ourselves before we move on, a C string, which is of which the correct data type is a char pointer, is a continuous sequence of bytes up to and blah blah blah, including the null byte at the end. Well, there it is, that's the second byte in, that's why you get a 1-byte string. Okay, let's start moving towards the real world and why this causes problems. Because some people might say, well, hang on a minute, isn't this all a bit nitpicky, you know, and if you know what your data type is, well, you know, then there's got to be an easy way around finding out whether it's wrong or not, isn't there? And the answer is yes, it's called compiler. And the compiler will tell you, with a warning, if you use data types that are incompatible or have a potential problem. And as we've seen right from the beginning of this presentation, they will cause an error if you use ones that are incompatible. Now, right from slide 1, we've seen that assuming that they are the same is an error. So there is an easy way, and the easy way is this. If you deliberately break those rules and deliberately describe data with an incorrect data type, and then force your code to use that incorrect data type, then you throw away those protections that the compiler gives you. You also throw away, if you're a library author, you throw away the protections that it gives to the people who are using your library, who are going to look at your incorrect data declaration and be confused by it, and then be forced to write incorrect code themselves because you've made an error in the way that you've declared your data and forced the compiler to ignore it by various sneaky tricks. So if you want those in, the simple solution is declare your data types correctly. Getting close to the real world now then. If you run any kind of half-decent web server on a 32 or a 66, you'll be familiar with that library stack. Well, at least the top 3. So your app calls ESP Async web server to serve up the pages. That in turn will call either ESP Async TCP library or or async TCP library. It's slightly confusing, but depending on which architecture you're using. Now, all the examples that follow, I'm using an ESP32, so I'm using async TCP. But the good news is that ESP Async Web Server just has a thing called an async client, and both of those libraries have the same interface, so it doesn't matter which one uses, which is why Async Web Server will compile correctly on a 32 and or a 66. Now, both, let's call that, just call that the TCP layer. The TCP application layer calls down into, ultimately, a thing called LWIP, which stands for Lightweight IP Protocol. And they do that via the Arduino core. Now, the reason I've got a diagonal line across the two there is because that's partly the GitHub project that you download into your IDE, and it's other partly a huge great binary blob that comes from Espressive that's got all the real nitty-gritty horrors in it that you can't see because you don't get the source code. It's proprietary. And that sits between the TCP layer and LWIP, which actually puts the data on and off the wire. That's excuse me, that's the device driver, if you like. So it's incumbent upon all these libraries then, because they're dealing with TCP data, it's incumbent upon them all to present the correct data type all the way up the tree so that your app can deal with the correct data type, and that any problems that ensue are then your fault, not the library author's fault. And unfortunately, that's not the way things go in the real world. So let's have a look at this little table here. Now, the first column is, from looking at the code of each of those, how they present to the next layer up, if you like, what their view of a block of TCP data is. Starting from the bottom then, we've got LWIP, which tends to be fairly stable. Yeah, I've seen bugs in it, but I've never come across a bug that in LWIP that's actually caused a problem to any of my code or any library code that sits above it, so it's rare. So LWIP is, you know, it's at ring zero, it's trusted, it works, and it correctly defines the data type as void. Hang on a minute, Phil, I thought you said it was uint8. Don't forget, LWIP is a general purpose piece of code that can be implemented on a number of different MCUs. All right, and therefore what it's telling you with void, which is 100% correct definition, is that no assumption can be made or is made by the underlying code about the nature of the data that is pointed to. Now then, at the next layer, where you are then providing the code that implements that on a specific MCU for which you do know the data type and therefore can make the assumptions, and in fact they're not even assumptions, they're absolute assertions. You know that all the memory and the heap and the stack inside the 32 and the 66 are 8-bit byte addressable. Therefore, the pointer to a block of TCP data in their memory will be, oh dear, it's a uint8 pointer. So why is that a char pointer? Well, it's quite an easy answer. It's wrong. Okay, that data type is wrong. It should be a uint8 pointer. And by getting it wrong that low down, you propagate that wrongness up the stack to the point where your app then has to use the wrong data type because everything else below it uses the wrong data type, because whoever made that decision there is, quite frankly, well, hopefully doing a different job now, because they shouldn't be doing that one, because that error is kind of fundamental. It's C101 we're talking about here. The correct data type for an unspecified raw block of data is a memory type pointer and a length. Excuse me. So let's continue to look up. Having said all that, again, there are sometimes occasionally problems in the core, but they're very, very rare. And 90-odd% of the time, it's going to be stuff above it, not this. So there's a questionable decision there, and because I can't see inside that blob, I don't know. Inside the blob, they might be right. It might just be like the GitHub layer on top that's wrong. But either way, at that point in the interface, the data type upwards is wrong. Now then, let's look at these other libraries then. Let's see what else they have in common, apart from having the wrong data type in them. Well, the first thing you're going to notice is that all of them have got async in the title. And when you truly understand what that means, you'll understand why in the UK we have a thing called the Trades Descriptions Act, and they'd all fall foul of that because none of them are actually async. They just kind of look like it in circumstances which most people use, where they're very, very lightly loaded and not at all stressed. Now I'm going to do a completely separate video on that trio of them there, and I'll explain to them how they're not async. I'm going to also explain why they're not async by looking into the code and seeing what it's doing wrong. And I'm going to show you some code that is truly async, and I'm going to run the two side by side, and you'll see in black and white proof why these things here are not truly async. At the moment, you just have to take my word for that. The other thing they have in common is that they crash if you push them beyond that limit of apparent asyncness. Mostly that's related to the fact that they don't do async properly. There's no direct link in there to say it's anything to do with the incorrect data type, because that would be a stretch too far. However, there are other libraries I've come across, one which I made 2 videos on already because there was so much in there to work with, and that actually did have some of the bugs, the 16 that I found in it, were directly attributable to an obvious confusion between the difference between a char pointer and a uintake t pointer, and it also wasn't async. So in my experience and my experience only, and again this is one of the very few opinion points here, I see a strong correlation between people who get their data types wrong, between a char and a uint, and people that don't understand async fully but write libraries with async in the name, all of which cause me a lot of problems at the moment. And that's why I've made this video, to try and make sure that people understand that subtle difference. So what we're going to do is start looking at some code very shortly, and we're going to run a couple of little programs which should amuse and entertain and shock as much as inform, I hope. Anyway, this is code from that async client, which isn't async, but never mind. We have a function called write, which takes a char pointer as data, no length, look, but oh look, it calls strlen. So this is obviously a string function. I'm happy with that. I don't have any problem with this code at all. This function expects a string, and we know that it expects a string because if it isn't given a string and you call strlen on it, bad things are going to happen. So that's a string function, and it's called write. Now this is where this confusion starts to come in, because there's also a function called write taking different parameters, what we call in the business an overload, which takes a const char data and a size t of size, and some flags which are irrelevant to this discussion. However, why do you need 2 separate functions for the same data type, one without a size and one with a size? Now, that's a kind of rhetorical question, because I know the answer, and you should already know the answer as well. But just to remind us, I'm going to pop in, oops, that's how confusing it gets, you see, it made me do the slides the wrong way. I'm going to pop in the function that both of these call as soon as they exit. They both a thin layer on the TCP write function of lwhip, which takes, no surprises there, look, a void pointer, because TCP write, lwhip, the correctly implemented library, makes no assumptions about what the data is. We, however, are now making an assumption that in this case where it's a string, that it will be a const char data. In this case where it obviously isn't a string, otherwise why would we need 2 calls? If it was a string, we could just call the first one, couldn't we? So this obviously isn't a string, but we refer to it with the same data type. Can you see the confusion that this starts to cause? Because while it's impossible to say that the first one is wrong, it is absolutely confusing when looked at with the second one. Because the first one, I have no problem with it. as a string function. The problem I have is that it calls the overload with effectively what is a different data type. Oh, but they point to the same place in memory field. Yes, I know they do. That's not what we're talking about. We're talking about the meaning and the intent of these. Because now we look at this second one, and it is quite clear that I would go up against anybody and say that that one is wrong. And it's because that one's wrong that it makes that other one confusing. Because that should be a uint8 pointer. And because it isn't, the author can get away with slipping in things like that as a nice quick overload to handle a string. Now, there's two problems I have with that. One, it's lazy, which is a kind of subjective argument. Two, it's wrong. The data type is wrong. It causes confusion, it's inaccurate, and when somebody that understands the true difference between the two tries to use that, they are then forced to coerce their correct data into this library's wrong data type, and that is what makes it wrong. And just in case anybody thinks that this again is an opinion piece, let's just remind ourselves of what TCP data consists of, and it is continuous unstructured byte stream, which is kind of exactly the opposite definition of what a C-style string is. It's a big lump of data. And char pointer is not the correct data declaration for a big lump of data, especially when there's a perfectly valid one which is correct, which is a uint8t pointer. Here we are then looking at some code which we can run, which kind of mimics the async code we were looking at in the last slide. Now, obviously I've greatly simplified it, but the first routine I'm calling swrite because it is clear from both the data definition on input and the fact that we call strlen and what you see being done with the data that it expects a C-style string as input. And what it does with the data is just prints the length of it, its address in memory, and it prints it as the standard string representation of a C-style char pointer. Now, rather amusingly, I thought, instead of having the second overload called write, I've called it wrong. And that's the one with the const char data as the data type, which is wrong, because the correct one, the right one, should be the one with the const uint8t data. And very shortly we're going to come to the implications of that difference. Both of them call the final destination, which in the real world is the LWIP thing. And here's the final destination with its correctly implemented void data pointer. And because it can make no assumption, indeed by using void it tells you it's not going to, all it can do is treat that data as a big block of data and a length, which is kind of good news because that's what it is. And it just prints out each byte in the input stream showing its visible character and its numeric value. And that's all there is to it. That's all we're going to do. And the first thing we're going to do is we're going to call this swrite to write these following strings. So we've got string C, fill in lowercase, and then we've got the second string here, string B, which is kind of like the first one, but it's got uppercase letters instead of lowercase. Lowercase, you know what I meant. And then we've got this thing here defined as uint8, this string U, which is 4 bytes long, kind of like these other two. Now, if as an experienced programmer you've already got alarm bells going in what I've said there, then good, because that means you're going to score 3 out of 3 in the quiz that's just about to follow. If you don't understand what I just said there, or can't see what the problem is yet, or still think that these two things are the same, then this is for you, and you're not going to score 3 out of 3. But the rest of the code, look, is structured as a series of questions, and the first 3 things I do is I call this swrite on string C, string B, and I have to force it, because the data declaration is wrong, I have to force it into what it thinks the data declaration should be. Now, the reason why this one here isn't a const is because I wanted to put some data in it at runtime, because if for some strange reason it turns out that these 3 things are indeed very different beasts, it makes it very difficult to demonstrate it if they all contain lowercase phil. So I've put uppercases in the second one, and I've put Dave in the third one. And because I'm doing that at runtime, I can't declare it as a const, and that's the only reason that isn't const. Otherwise, everything else is the same. But I'm just doing the magician thing of showing you there's nothing up my sleeve. Okay, so let's just do a hard reset on this ESP32 and get that code running. So there's our first question that comes up. And read the question carefully. How many bytes does strc occupy? If you're having any problem answering that at all, or you think that the answer is 4, then read the question again very carefully. How many bytes does it occupy? Not what is the string length of it as a string, as a C string, which we know it is, because that's obviously 4. PHIL, 1, 2, 3, 4. It occupies in memory 5 bytes because it has to have that trailing null, which is what makes it a string. And if it wasn't, then that strlen function wouldn't work. So apart from me being deliberately pedantic and asking how many bytes, if you said 4, I'm going to give you a point anyway, okay? And there they are, no surprises, PHIL. It even comes out looking like a string when we put it in the %s of the printf. Everything is happy. That's exactly the way we expect to see it. What on earth fuss is all this about, Phil? Let's look when we answer a very similar question about strb. So, how long, what's the length of strb? And the really smart amongst you are going to be going, oh, hang on a minute, this is that trick question again, isn't it? What you're really asking here? And I'm asking how long, what's the length of it? As it depends what you mean by length, doesn't it? It depends how you interpret that question. What do I mean by the length? Do I mean the length as a string? Do I mean how many bytes in memory? Who knows? Well, let's not waste everybody else's time. Let's see what the computer thinks. Whoa. Now my prediction is that quite a lot of you are going to be surprised by that result, which is great because that's who this video is for. Because anybody who isn't surprised by that result will be thinking, why are you telling us all this? This is obvious, Phil. Well, it's good. It's good for you that it's obvious. You aren't the problem. Why are we getting this? Let's have a look. Let's do some diagnostics on it. Most of you probably expected that to be 4 bytes long and say fill in uppercase. Well, look, it does. It does to start with. But then what's this other stuff? Oh, look, it's fill in lowercase. We've seen that before already, haven't we? That's why I printed the address of these things here, people. Because this starts at 0316. Don't forget, this is all in hexadecimal. So 316, 317, 318, 319. That would be address 31A. And lo and behold, that is the address of Phil. So that absolutely is where the compiler has put that first C string of Phil. And this blank line here would be where the null byte is that makes Phil a string. Because when you start at its correct address, you find a null byte here at whatever the address is. I can't be bothered to work it out. Whatever that is, plus 4. But because you're starting at a lower address here, which is where the real 4 bytes of fill live. Note what I said there rather carefully. That's 4 bytes of fill. That second definition, strb, is not a C-style string. It is a block of bytes, which you know, because you wrote it, to be 4 bytes long, containing an uppercase P, H, I, L. There is nothing in that syntax that tells the compiler it is a string. Right? That is the definition for 4 independent bytes, and you have chosen to call it a char, which is incorrect. But there's no way the compiler can know that that's incorrect, because it doesn't know how you're going to use it. Because if you use it as a string, when it isn't a string, that is why you get that error. Because by telling your code that that's a string, it will say, right, well, I'm just going to keep on chuntering till I find that null byte then. So I'm going to start at this address here, and I'm going to keep on going. It happens, thank you compiler, I wish I could pay it for doing this, that the very next block of memory is that one that you've already created called fill. I couldn't have designed that better, but it actually happened by accident. But it shows perfectly the problems you get by confusing a string with a block of bytes. It also should start showing you why I chose Dave for the third one, because now we're going to come up and ask, what's the length of stru? Now, if you're not ready for a surprise here, you probably haven't been listening. But I'm going to give you a second or two to guess what the length of stru is and what its content is. Now, did any of you predict that? What we've got there is the same problem, albeit we're in a different area of memory. And again, that's why I put the memory address pointer is because it's not fill that follows it here now. Again, thank you compiler, it's random gibberish. Just so happens, you can't make it up, that the exact number of gibberish bytes before the first valid null is 4. It kind of makes it look like there's some pattern going on here when there isn't. It's just pure coincidence. But again, all that says is this is a block of 4 bytes. I filled it with 4 bytes of data. It just happens that 8 bytes on, there's a null. So when I incorrectly treat that as a string, it doesn't stop until it gets to the null. Now then, here's the ultimate point I'm driving at, if you haven't already got it. Let's look at what we had to do to get that to even work. We had to say, even though I know an stru is actually a block of bytes, and I know it's 4 lines long, if you're saying you can handle it with an swrite, now don't forget, I've seen under the hood here. I know the problems with this library. I know what's wrong with it. I know the errors in it. And I've been doing this a long time. So I know that that's going to fail. But how many people, taking that at face value, with an incorrect data definition of char pointer in there, how many people are going to say, well, okay, well, if I do this, that'll get it through, won't it? Yes, it'll get it through. It'll get it through compile, but it will fail when it runs. And that's the problem. Now then, that there is the first sign that any decent programmer should have, is that there's something wrong somewhere. This is what's known in the business as a code smell. That's a bad smell. And winding right back to the beginning of the presentation, and I showed you that error that proves you're wrong, doing it the other way round is what produces that error. So what we're doing here is we are trying to coerce a uint8t pointer to a char pointer, and we got away with it. Now, had I put the warnings on, I might have even seen there's a warning, but I don't generally want warnings on. I generally ignore warnings because I know what I'm doing. So when I get one, I know the implications of it. However, the point is, were you to do that the other way round and try and coerce a uint8t pointer to a char pointer, whatever it was, that's an error. The compiler will say to you, yeah, hang on a minute, are you sure you know what you're doing here? And if you're writing code like this, the answer to that is an unequivocal no, you don't. Again, that's why I'm making this video. But let's move on. If we are to use the code we've got up there, we would have to do something like this with it. We would have to, it can only work without mucking about and getting a correct compilation by using the right data definition that matches the type of what we're sending it. Which is why when we run this next final part, then it actually does exactly what you'd expect it to do, because the data definition of that matches the data definition of that, and the data definition of that is correct. And when you get your data definition correct and your data correct, because it's forced to be, otherwise you have to do the kind of nonsense we've seen already, like this. Once you get them both right, lo and behold, the code does kind of what everybody would expect it to do. Now, to show you the final part, to ram the point really home, I have to recompile this, so I'm just going to pause. Now, the obvious extension of knowing that this one was correct with stru would be then that we'll use this right function, because it's right, on strb and strc. But look what happens when we try. We get that message. Is that familiar to any of you? That says that you are trying to convert a const char pointer, which is the definition of strc, to a const uint8t pointer, also known as a const unsigned char. So the absolute difference in true terminology between the two is that a char pointer, as Mr. Lawson suggested in there, has no sign, but an unsigned has an unsigned. So you're converting an unsigned, trying to convert a data type that has no concept of sign into something that's unsigned. And by definition, that's wrong. The wrongness of it being that the compiler isn't even going to continue and try and compile it because it can't, because it makes no sense at all, because the data types are incompatible. So what you can see here, which might look like the seeds of doom, is in fact the seeds of the answer. But because by providing the correct data type in our function, and we know that we have because when we give it the correct data in stru, it works exactly as expected. When we give it the wrong data type, compiler says, that's wrong. So we've got to fix this. And how do we fix this? We've got two ways of doing it. We can either cheat and be slack and do it the lazy way and force them to be const uint t pointers. Now that's a sticking plaster solution to the problem. But it saves time. We're long enough already on this video. So we'll get rid of the bad one and we'll get rid of the good one. The real answer is that we should go back and we should redefine the data types of strc and strb correctly. And if we were to do that, we would find this, which kind of pulls everything together that I'm talking about. If we did that, if I changed that to uint8t like these others, that would then fail the compile in its own way, because it would say, hold on a minute, you're trying to assign what is a C string here to something that's declared as uint8t. And you know what? If you've been listening so far, you'd be going yay, yay, yay for the compiler, because that's exactly what you want it to tell you. You want it to tell you this is the wrong data type for this type of call. And we know it is, because all the way through this presentation we've been talking about the fact that this is data that's going into a TCP buffer. I mean, obviously the compiler's not psychic, it doesn't know that. But by putting the correct data type on the function call, it now knows that the data you're trying to give it is the wrong type, and it will object. And that will make you rewrite your code so that it's correct. So do you see the point of this whole presentation? Let me just compile this as we're talking. The point is this, that in terms of style be buggered. We're talking about accuracy and correctness. By using the correct data type for that library call, we force everything above it to also become correct. And if we don't do that, the opposite happens. If we choose it wrong, we force everything above it to be wrong, and cause errors and problems of the type that when you put the correct definition in, here's all the wrong ones, we know these aren't going to work. When you have a correct data type definition, you get the correct expected answer. And that, dear friends, is the difference between a char pointer and a uint8t pointer. One of them's wrong for this type of data, and the other one is correct for this type of data. Don't take my word for it. Take the C compiler's word that tells you in bold and plain English incompatible conversion between two data types. Hopefully now you understand why. Hopefully you understand the implications thereof. Because unless you do, when you use a library that, like these libraries, all use the incorrect data types, they lead you into using the incorrect data types, and they also, if you look carefully at the code, they also lead themselves into making some quite silly mistakes in those libraries and providing features that shouldn't be there, that kind of compound the error of convincing you that everything you're dealing with was a string when the exact opposite is true. And if that isn't by definition confusion, I don't know what is. So while we can all agree that the two different data types have the same data width and occupy the same amount of space, they are significantly different in their meaning and usage. And you get them wrong at your peril if it's your own code, and every other poor bugger's peril that uses your code if you publish it. And if you do publish code like that, perhaps that should go into the rant series of videos of what I think about people that do. I hope you found this useful and educating, and I hope you will now go and kind of give it the rah 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 to anybody else who wrongly thinks that a char pointer and a uint8 pointer are the same thing. Thank you as always. As always, thanks for watching. Please remember to subscribe, like, click the notification button and support me on Patreon if you can. Thanks, and see you next time.